Hello everyone, this is Professor Roman, and I want to continue the lecture series on linear algebra. Today I'm going to do something a little bit different. It's a bit of a digression. It's not something that I can do in a physical class in linear algebra because there just isn't time, and because it does and will take us outside the scope of linear algebra per se. So I don't imagine it's something that's covered very often in any linear algebra course. But I think it's very important because it will give you some context. It'll put the subject of linear algebra in a somewhat broader context. And it'll point out an issue that I would guess is seldom addressed in linear algebra courses, for reasons I'll discuss at the appropriate time. So we have seen that if S is a subspace of an inner product space V, then the orthogonal direct sum, S orthogonal direct sum S perp, always exists. But it may fail to be all of the inner product space V. However, if S is finite dimensional, then the projection theorem does tell us that V is the orthogonal direct sum of S and S perp. And that is because the Fourier expansion of every vector with respect to any orthonormal basis, they're all the same, is in fact the unique orthogonal projection of V onto S. So we can decompose V in this manner. This holds for any vector V in capital V, and it gives us this decomposition. We can also say that the Fourier expansion V hat is the unique best approximation to V from within the subspace S. And also that V hat is the unique vector, say W, in S for which the residual V minus W is orthogonal to the subspace. On the other hand, we've also seen that for the inner product space L2, the projection theorem fails. When S is infinite dimensional. In fact, when S is this particular subspace, spanned by the standard sequences with a 1 in a single place and zeros everywhere else. When S is this subspace, because this subspace, this is the sequences with finite support, has trivial orthogonal complement. So this sum is not equal to all of L2. So all this is stuff we discussed in the previous lecture or so. Well, the question now is what went wrong in L2? Clearly it has something to do with the fact that the subspace S is not finite dimensional. Turns out that the answer to this question has far-reaching consequences, and as I mentioned, is not something that's discussed, I think, in general in linear algebra courses. The short answer to what went wrong is that the concept of a basis is simply not strong enough to produce orthogonal projections when the subspace S is not finite dimensional. Now, since there's a great effort is spent in the first part of any linear algebra course to convince students of the importance of bases. I think a professor is naturally somewhat reluctant to criticize bases. So I think that's a minor issue, really, I guess. The real reason for not delving into the problem with bases is that it leads the discussion away from linear algebra per se and into a different branch of mathematics called functional analysis, and in particular to the study of Hilbert spaces. And so there either isn't time or isn't motivation or both to go in that direction. But we will do that now. This lecture, and if it takes 2 lectures, then the next one, are not critical to an understanding of the future lectures in this series, and so if you're not interested in this, you can skip this lecture. A related problem with bases is the following. For vector spaces of uncountable dimension, all bases, of course, are uncountable, but uncountable bases, such as those for important vector spaces like L2 and also CAB, the continuous functions on the interval AB, seem to be impossible to find. And even if they could be found, would be way too large to be of any real use. Uncountable bases are not of much use, if at all. In order to find a substitute for uncountable bases, and in order to extend the projection theorem to all subspaces of a Hilbert space, we have to turn away from bases and towards maximal orthonormal subsets, which we've already discussed. We know from Zorn's lemma that every Hilbert space, every inner product space, in fact, has a maximal orthonormal subset. We will see that maximal orthonormal subsets are capable of expressing every vector in a Hilbert space not as a linear combination of basis vectors, but as a limit of linear combinations of vectors in O in the orthonormal subset. I guess I can use the term here Hilbert basis because we've already discussed that. So we're turning away from Hamel bases. Uncountable Hamel bases are insufficient to do what we need to do. We have to turn to Hilbert bases. Since we're going to be dealing with limits, we have to discuss convergence. We don't have to go into great detail, but we do have to cover some basic concepts. And these matters require only the presence of a metric, so we may as well work in the general context of metric spaces. This actually will be simpler because we don't have any extraneous structure like inner products and so on to get in the way of the concepts. But of course our main goal is to study Hilbert spaces briefly, and those are inner product spaces. So here we go. Convergence in a metric space is defined as follows. A sequence xn in a metric space M converges to an element x in M, and we write it in the usual way if you're familiar with sequences of real numbers. if the limit of the distances from xn to x is 0 as n goes to infinity. So the distances approach 0. And more formally, it means that for any epsilon greater than 0, there is a capital N greater than 0, such that if little n is bigger than or equal to capital N, so we're out far enough in the sequence, the distance between xn and x is less than epsilon. It's a key fact that the inner product is not only sesquilinear, but it's continuous in both components under the metric defined by the inner product. Let V be an inner product space. The inner product is continuous in each component separately. Specifically, if the sequence UN converges to U in V, then UN inner product with any vector V converges to U inner product V, and similarly when you put the sequence in the second component. From this, it follows that the norm is also continuous. So that if xn converges to x, then the norm of xn converges to the norm of x. And this is a consequence of the Cauchy-Schwarz inequality. The absolute difference between these two inner products, UNV and UV, can be written this way because of the linearity in the first coordinate. And the Cauchy-Schwarz inequality tells us that this in absolute value is less than or equal to the product of the norms. The norm of V is fixed, but the norm of UN minus U tends to 0. That's the definition of the distance. It's the definition of continuity. I'm sorry, definition of limit. Okay. And it works the same way for the second component. Here we have the first result that ties together the algebraic structure and inner product and the analytic structure, the convergent structure. We are tying together, in a sense, two different branches of mathematics. This is very common. I probably said before, I know I've said it many times, I think I've said it in this lecture series, branches of mathematics do not stand in a vacuum. There are many connections, and those connections are very fruitful and develop whole other areas of mathematics. The combination of two areas of mathematics can produce an entirely new area. Convergence can be used to define the notions of closed set and open set in a metric space. A subset C of a metric space M is closed if whenever a sequence in C converges in the whole space M, the limit actually belongs to C. Another way to say this is that C is closed if and only if it is closed under the taking of limits. So that's analogous to closure under addition or scalar multiplication. A subset of M is open if its complement is closed. There are other definitions. If you've studied metric spaces, you may have very well encountered a different definition of these concepts. You may have encountered the definition of open set first, and then sets are closed if they're complement or open. So there are many ways to approach this, but my choice was to do it in such a way that we can get back to the subject at hand as quickly as possible. Examples. If a and b are real numbers, the closed interval AB is, well, closed under this definition. But the half-open interval, if you open either one of these endpoints, it's no longer closed. The set of rational numbers fails to be closed in the metric space R. Well, R we always assume has the usual metric, absolute value of the difference, unless we say otherwise. So, to illustrate, all we have to do is take an irrational number, such as the square root of 2, and take the sequence of truncated decimal representations of square root of 2. This sequence is converging to the square root of 2, but the square root of 2 is not rational. So we have a rational sequence converging to a non-rational number. So the rationals are not closed. Neither is the set of rational numbers open, because its complement, which is the set of irrational numbers, is also not closed, and I'll let you think about that. So Q is neither open nor closed in R. Now, any subset S of a metric space M is contained in a smallest closed set, and that is called the closure of S. Obviously, if S is closed itself, then its closure is equal to itself. But there is always a closure, unique closure. This too can be defined in different ways. One way is to define it to define the closure as the intersection. It is the intersection of all closed sets containing the set S, or one way to produce the closure. But that's not the way we want to proceed, because, as I said a minute ago, we want to go as directly as we can to the important points here. So this is the definition I've chosen, and others do as well. If S is a non-empty subset of a metric space M, then the closure of S, by definition for us, is the set of all limits of sequences in S. And we'll denote it by CL of S. The elements of S belong to the closure, because if X is an element of S, you can just take the constant sequence, every term of which is X, that converges to X. So it's a limit of elements of S. Yeah. Another notation for closure is S over bar. But I chose this one for this class because I think it's a little easier to remember. You don't have to remember what the over bar means. CL is a good hint that it's the closure. So that's why I kind of like this one. If I was teaching a class in metric spaces or topology, I might prefer S bar. And I'm going to let you think about why this definition of closure does give you the smallest closed set containing S. There is some work to do there. Example, in the metric space R, the closure of the set of rational numbers is in fact all real numbers, because for every real number R, there's a sequence of rational numbers that converges to R. We did that already for the square root of 2. It works for all real numbers. So the closure of Q is R. The closure of a non-empty open interval is the closed interval. That's where the term closed interval comes from. If X is a subset of an inner product space V, then we will denote the closure of the span of X by C-span X. Again, that's a fairly descriptive notation. One wouldn't want to confuse it with the television station of the name C-SPAN, but I don't think there's too much danger of that. If a vector V is orthogonal to a subset X, then the sesquilinearity of the inner product tells us that V is also orthogonal to the span of X. And the continuity of the inner product will then tell us that the vector V is orthogonal to the closure of the span, C-span of X. And that's going to be very important for us. So here's the theorem. Let X be a non-empty subset of an inner product space V. X perp, the orthogonal complement of X, is a closed subspace of V. We already know it's a subspace. We discussed that. The orthogonal complement of a subset is a subspace. But here we're seeing that it's also closed. As a consequence of that, if little v is orthogonal to every term in a sequence in the inner product space that converges to some limit w, then v is also orthogonal to the limit. And the orthogonal complement of C-span of X is the same as the orthogonal complement of X. So let's look at the proof. For part 1, which is that X perp is closed, as I said, we know that's a subspace of V. If Xn is a sequence in X perp that converges to a vector V, we need to show V is also in X perp, then the continuity of the inner product tells us that for any X in the subspace, in the subset capital X, the limit of these inner products is the inner product of the limit, but X is in capital X and V and Zn is in X perp, so each of these is 0. X is in X, Zn is in X perp, so each of these is 0, so the limit is 0, but the limit is also, the limit of the inner product is the inner product of the limit. We can pass the limit inside because of the continuity, so we get the inner product of V and X is 0. So V is also in X perp. Okay. So the limit of a sequence in X perp is also in X perp, and that means X perp is closed. For part 2, we have this vector orthogonal to every term in a sequence that converges. Then it's also orthogonal to the limit. Well, the sequence is then orthogonal to V, which means it's in the closed subspace by part 1 of the set V perp. So this is just a singleton set, in this case, orthogonal complement. So by part 1, the limit is also in V perp, orthogonal to V. So V is orthogonal to the limit. And for part 3, of course, X is contained in the closure of the span of X. In fact, it's contained in the span of X. So when we take orthogonal complements, that reverses the inclusion, so the C-span of X perp is contained in X perp. The converse is a tiny bit more work. If we take a vector in X perp, we call it V, then of course it is in span of X perp. Not C-span, that's what we're trying to show, but span of X, these are just linear combinations of vectors in X, so V is orthogonal to any linear combination of vectors in X. And so V is orthogonal to the limit of any sequence from here. In other words, it's orthogonal to everything in C-span of X. So we have this equality. And if you want to, you can stick the span of X perp in there too, okay, because it falls in between these two. To say that every element of a metric space M is a limit of elements from a subset, S of M, which is what we want to be able to do, that's simply to say that the closure of the subset S is all of M. So closure is precisely the concept we need here to express the fact that we can get everything in M as a limit of a sequence from S. And that has a terminology. A non-empty subset S of a metric space M is dense in M if the closure of S is all of M. We've already seen an example of that. The closure of Q is R. So the rationals are dense in the reals. Of course, any metric space contains a dense subset, the whole space itself, but that's essentially useless. The useful dense subsets of a metric space are those that are relatively small and relatively easy to describe. And that prompts a definition. A metric space is said to be separable if it contains a countable dense subset. So the real line is separable because Q is a countable dense subset, and similarly the Euclidean spaces Rn are separable. Qn is a countable dense subset. Complex plane, the complex numbers are separable, and so are the unitary spaces. The inner product space L2 is also separable. This, again, is L2 of R, the square summable real sequences. To find a countable dense subset, we take these sequences. They terminate at some point, well, that's not the right word. At some point they become all zeros. And the non-zero entries are rational. So if you take all of these sequences, this is a countable set. And we can show that these are dense in L2. Any element of L2 is a sequence that is square summable, So that means this sequence converges. So for any epsilon greater than 0, there is a capital N such that the n plus first tail of this series, which is this sum here where you start at n plus 1 and go to infinity, this can be made as small as we want. So we'll make it less than epsilon squared over 2. What to do with the first portion of this sum that's not part of the tail? I guess you could call it the head of the sequence. Well, the rational numbers are dense in the reals, and so we can find rational numbers, q sub I, such that this difference squared is less than epsilon squared over 2n for I going from 1 to capital N. See, we have to have a finite number of these, otherwise it's not going to work. So that's why we chop off the tail separately. We deal with the tail separately from the head. So, what about this sequence, which belongs to our subset, or countable subset, we're trying to show is dense? Well, the square of the distance, I can split off again the tail of this. This would be the sum from 1 to infinity of this expression here, but I'll split it into 2. In the tail, the q's are all 0, so I don't have to write them here. So I get these two sums. This one, each of these terms is less than epsilon squared over 2n, and there are n of these terms, so this sum is less than epsilon squared over 2. This one is also less than epsilon squared over 2, so this whole expression, this distance squared, is less than epsilon squared, so the distance from x to s is less than epsilon. So that shows that there is an element of our countable set S that is arbitrarily close to any element of L2. In other words, S is dense in L2. And so it's also separable. So L2 is separable. It might be worth pointing out that this set, which we have been interested in the past, these, remember, are the sequences that have a single 1 and all zeros otherwise. This set is not dense in L2. There are sequences in L2 that are not a limit of these sequences. But the span of this sequence, the linear span, is the sequences with finite support that is dense in L2. But it's not countable. So I guess what I add here is a display. C span of O is L2, the closure of the span. That's what it means to say that the span is dense. Its closure is all of L2. Well, this example shows that even though the vector space L2 has uncountable dimension, and so its bases, if you can find one, are of little or no use, it does have what we would consider to be the next best thing, namely a countable dense subset. A countable set for which every element of L2, every vector in L2, is a limit of a sequence from L2. Unfortunately, not every important inner product space is separable. And just to emphasize that, if an inner product space has an uncountable orthonormal set, which I wrote this way, then V is not separable. The problem is that, I'll just skim over this. The problem is that if you take two vectors from this set, because they're orthogonal, orthonormal in fact, their distance, the distance between them is the square root of 2. So as I think I discussed briefly before, vectors in an orthonormal set are spaced apart. They can't be too close together. So we can find little balls around each one of these vectors, or little disks if you prefer that term, that do not intersect, that are pairwise disjoint. And there's uncountably many of those. So no countable set can be dense, because to be dense there would have to be an element of the set in each of those balls. But there are uncountably many balls and only countably many members of the subset. Okay, now it's time to define completeness for metric spaces. Officially. I talked about this before, of course, very briefly. Sequence xn in a metric space M is a Cauchy sequence if the distances between the terms of the sequence approach 0 as we go further out in the sequence. So that's an informal way to express it. Formally, for any epsilon greater than 0, there is a capital N greater than 0, such that if we have two indices, n and m, both past capital N, the distance between the sequence elements is less than epsilon. It's vitally important to recognize that a sequence can be a Cauchy sequence and yet not converge. And an example is found in the metric space Q of rational numbers. So for a moment, this is our universe. Nothing else exists. Non-rational numbers do not exist. It's not part of our universe Q. But this sequence of rational numbers is a Cauchy sequence. These terms are getting closer and closer together, but they don't converge to anything. If we expand our universe to R, then this will converge to the square root of 2. But that's not relevant to the question of whether Q is has the property that Cauchy sequences always converge. The answer is no. It's pretty easy to show, it would be good practice to show that any convergent sequence is also a Cauchy sequence. If all the terms in a sequence are heading towards a single element, then they're getting closer together. That's not a proof, but it does seem rather clear. A metric space is said to be complete if every Cauchy sequence does converge, and by that it must mean converge to an element of the space. And I should say subset here really, and a subset S of a metric space M is complete if it's complete as a metric space in its own right. I don't know if I said this, I don't think I did, but if M is a metric space, any non-empty subset is also a metric space. Same metric. this is a very useful fact. Before we look at examples, I want to go over this. If M is a metric space, any complete subset of M is closed. So if you have a complete subset, that means every Cauchy sequence converges, or let me say it more clearly, any Cauchy sequence in the subset converges to an element of the subset, then that subset is closed. If M itself is complete, a complete metric space, then a subset S of M is complete if and only if it's closed. So in complete metric spaces, the subsets, for the subsets, these properties are equivalent: completeness and closedness. And I'm going to skip over this proof. If you have the book, you can read it, of course. But I think this would be a real good theorem for you to try to prove, to see if you can crystallize some of these ideas. Let's look at some examples of complete metric spaces. This is my attempt at humor. For completeness, we'll repeat example 524. The real numbers R and the complex numbers C are Hilbert spaces. They are complete inner product spaces. As to the proof, that's a bit tricky. Once we prove the real numbers are complete, proving the complex numbers are complete, it's not that difficult. But the proof that the real numbers are complete is intimately connected with the definition of real numbers, and that's something we can't get into because it would take us too far away from. We're going far enough away from linear algebra as it is, but this would take us even farther away, so it's not appropriate. So you just have to take my word for it at this point. The rational numbers do form an inner product space, but it's not a Hilbert space because it's not complete, as we've seen this sequence. L2 is complete. We've already shown that L2 is separable. We can now show that it's complete, making it a separable Hilbert space. To prove this, we need to show that any Cauchy sequence xn in L2 actually converges. So I write each term xn of the sequence this way: xn1, xn2, and so on. For each coordinate position in this sequence xn, so this is a little bit testy because we have a sequence of sequences, okay? Each xn belongs to L2, so it's a sequence, and we have a sequence of sequences. But the difference, the absolute square difference of two terms at the same location in xn and xm, in the same position, this is less than or equal to this expression, which is the square distance from xn to xm, and that goes to 0 because we have a Cauchy sequence. So the sequence we get by extracting from each of these its ith coordinate, same coordinate in each case, this is a Cauchy sequence in R. So if here's x1, you write it out, here's x2, you write it out, and so on, and you just grab the ith coordinate. That is a Cauchy sequence of real numbers. And since R is complete, those sequences have to converge. So this whole thing converges to y sub I. In each position, each vertical column converges. And so what we need to show is that the sequence of limits there, which we'll call just y, is in L2, and that the original Cauchy sequence converges to y. And so that's what's going on here. This is the consequence or the definition of Cauchy sequence. And if we let m tend to infinity, we get this inequality. And then letting r go to infinity, we get this sum. And that tells us that this sequence xn minus this sequence of limits is in L2, but this sequence is in L2, so this one is also. And writing y this way tells us that, I just said that really, y is in L2, and that the xn's converge to y. Okay. Now we can talk about Hilbert space. Since an inner product space is a metric space, what we've talked about so far applies, of course, to inner product spaces. An inner product space that's complete under the metric induced by the inner product is called a Hilbert space. This we already knew. Hilbert spaces play an especially important role in both theory and applications. As a matter of fact, Hilbert spaces are the appropriate setting for quantum mechanics. The possible states of a quantum mechanical system are symbolized by unit vectors that are called state vectors in a complex, separable Hilbert space. That's called the state space of the system. And that's all I'm going to say about quantum mechanics. Although certain types of linear operators, bounded linear operators in particular, on the state space are also critically important. They're called observables, but I wasn't going to say that, so scratch it. We have mentioned already that Euclidean spaces and the unitary spaces are Hilbert spaces. Any finite dimensional inner product space is a Hilbert space. So that tells us that we are, in fact, generalizing finite dimensional inner product spaces by studying Hilbert spaces. And L2 is a Hilbert space. In fact, these L2 spaces, and there's more than just L2 of R and L2 of C, they're the prototypes of all Hilbert spaces. They were introduced by David Hilbert himself in 1912, and it can be shown that all Hilbert spaces are isometrically isomorphic to one of the L2 spaces. So we haven't discussed what that means, isometrically isomorphic. It will come in the next chapter. But basically, an isomorphism between vector spaces preserves the algebraic structure. An isomorphism between inner product spaces has to also preserve the inner product. And those are called isometric isomorphisms, to distinguish them from linear isomorphisms. We can now rephrase something earlier. A subspace S of a Hilbert space H is a Hilbert space itself if and only if it's closed. So it's the closed subspaces of a Hilbert space that are also Hilbert spaces. They're always inner product spaces, closed or not, but the closed ones are the Hilbert spaces. And we could just from now on say closed subspace of H, but some do, and I will refer to them as Hilbert subspaces for emphasis. Okay, now we are ready. We've covered the background information we need to address the problem at hand, and that's the projection theorem. And we're going to do that in two stages. We're going to look at the countably infinite case first, and then we'll discuss the uncountable case, and I'll explain what those mean in a minute. In the countably infinite case, we're going to be dealing with countably infinite sums. And so questions of convergence will arise, and we need a couple of preliminaries. As you may know, a series of real numbers converges absolutely if this series converges. In other words, the series consisting of terms that are the absolute value of the original series. Also, this series converges unconditionally if any series that you can form by rearranging the terms in this series also converge. It is a theorem in real analysis that a series converges unconditionally if and only if it converges absolutely. I don't know whether that's proved in general in an undergraduate analysis course or not. It was when I was a student, but that was a long time ago. The following theorem, along with Bessel's inequality, are the keys to the countably infinite case. This theorem says the following. We have a countably infinite orthonormal set in a Hilbert space. Then this series, this is what you might call an infinite linear combination of these vectors, converges in the Hilbert space H if and only if this series converges in R. We're taking the norm squared of each of these terms, so those are real numbers. If these series do converge, then they converge unconditionally. Clearly this one converges absolutely and therefore unconditionally, and therefore so does this one. You can rearrange the terms here and still have convergence. Therefore you can rearrange the terms here and still have convergence. And what I just thought of calling the extended Pythagorean theorem, I don't think that's a standard term, will hold, and that looks like this. If this was a finite sum, you would have, in particular of two terms, you'd have the usual Pythagorean theorem. Okay. So let's look at the proof. See, this theorem is tying in convergence of a series of vectors in an arbitrary Hilbert space to convergence of real series, and that's why it's so important. Let's denote the partial sums of this series by S sub n. So that would be the sum k goes from 1 to n of rk uk. And we'll denote the partial sums of this series by p sub n. Then for m less than or equal to n, the Pythagorean theorem tells us that this difference of partial sums of the original series here, norm squared, is equal to this. And now we can apply the Pythagorean theorem with n terms here, because UK is an orthonormal set, and that's critical to this theorem, becomes this, which is this. And so this tells us that the sequence of partial sums, S sub n, that go with this series, is a Cauchy sequence if and only if the sequence of partial sums for this sequence is Cauchy. So they're Cauchy at the same time. But both H and R are complete. H is complete, it's a Hilbert space, and R, we've mentioned, is complete. And so we can then say that this sequence of partial sums converges if and only if this one does. And that's the first part of the theorem. If the series if both these series converge, in particular this real series converges, then it converges absolutely, as I said before, and therefore unconditionally. And so the other series converges unconditionally. And finally, as to this extended Pythagorean theorem, this sum, which is a convergent sum, norm squared, is equal to this. I've just taken the limit as n goes to infinity of the partial sums. The norm is continuous, and so because we have a convergent sequence, I can pull the limit out, and now I can use the ordinary Pythagorean theorem, and then I can take the limit again. And that's how I get the extended Pythagorean theorem. Okay, so that's our key theorem. Now, as to the projection theorem itself, we have a Hilbert space H and a Hilbert subspace of, I'll call it S, of H. This is the setting for extending the projection theorem. The original projection theorem was valid in any inner product space. It didn't have to be complete, but the subspace S had to be finite dimensional. The whole purpose now is to extend that, and in order to do so, we have to work in a Hilbert space, and S has to be a Hilbert subspace. And suppose that S contains a countably infinite orthonormal set whose C-span is S. So this is what I mean by the countably infinite case. And we're going to talk more about this requirement later. It's going to turn out that this is equivalent to saying that the set O is a Hilbert basis for S. So it all generalizes nicely. Okay, but for now, since we're not quite ready to show that, we'll just accept this as one of the hypotheses. Our goal, of course, is to show that the projection theorem holds that H is the orthogonal direct sum of S and its orthogonal complement. Or equivalently, that for every vector V in H, there's a vector little s, depending on V, of course, for which the difference, V minus S, is in S perp. Because as we've done several times before, that means we can write V as S plus V minus S, and we'll have this decomposition. In more succinct terms, every vector V in H has an orthogonal projection onto S. Now, an earlier theorem tells us that the orthogonal complement of the C-span of O is the same as the orthogonal complement of O. So S and O have the same orthogonal complement. So this vector, V minus S, will be in S perp, which is what we're trying to show, if and only if V minus S is orthogonal just to the vectors in O. That's enough to make it orthogonal to everything in S. And this, of course, can be written this way. Well, so far, so good, and we're pretty much following the same pattern as we did in the finite dimensional case. But here's where things get a bit more complicated. In the finite dimensional case, we simply defined the Fourier expansion, and we showed that that would work for the vector S, that these equations would hold for all k bigger than or equal to 1. We can by analogy define V hat as this infinite series, but we can't just claim that that can be equal, that can be our choice for S, because we don't know whether this converges or not. That is the entire wrinkle in generalizing from the finite dimensional case to the countably infinite case. If we can overcome that, everything else is a go. So, and the reason is, if this does converge, let's assume for a moment it does, then these partial sums, which I called xn, converge to a vector S. And because these partial sums belong to the subspace, the Hilbert subspace, capital S, so does its limit, because a Hilbert subspace is closed. That's why this only works for Hilbert subspaces, equivalently closed subspaces. It doesn't work for all subspaces of a Hilbert space. Then for any k bigger than or equal to 1, if n exceeds k, then when we take the inner product of xn and uk, n is now bigger than k, so xn includes the uk term. When I take the inner product, I get v inner product uk. It just picks out the coefficient here. Okay. Taking the limit as n tends to infinity does not affect this side. On this side, we have, again, by continuity, that this is equal to, since xn's converge to S, this limit is equal to this. So that we have VUK unaffected by taking the limit. The limit is taken on here. Put the limit inside, we get SUK. So this is what we needed to show to complete the proof of the projection theorem. So all we are left with is the issue of whether or not this sum converges. But now we can apply an earlier theorem and leverage the finite dimensional case. The theorem we just proved tells us that this series converges if and only if the series we get by taking norm squareds are here. So it looks like this, that this converges. So all we have to do is show that this converges. Well, from the finite dimensional case, if we just take the subspace spanned by U1 through UN, call it S sub n, this is finite dimensional. And so the orthogonal projection of V onto this space is given by this Fourier expansion. I didn't want to use V hat here because I've already used it here. I could have called this V hat sub n, but there's not any point to doing that. This is the orthogonal projection of V onto S sub n. Now, the Pythagorean theorem and Bessel's inequality tell us that, I'll call this partial sum P sub n. I don't know, maybe I'll think about V sub n hat after all, and then I could put that here too. It's minor. In any case, this sum is equal to the norm of, if I take the norm of this, I get this sum, norm squared, excuse me, I get this sum. But Bessel's inequality tells us that this is always less than or equal, this is a projection, so its norm is less than or equal to the norm of the vector being projected. So what we have here then is we have these partial sums, and that's the partial sums of this series here that we're trying to show converges. These partial sums are strictly increasing because each term is non-negative, and bounded from above by the norm of V squared, and therefore converge. That's a consequence of the completeness of the real numbers. Actually, I said positive. I should have said non-negative. These are non-negative terms. So this is actually not strictly increasing. It's just increasing. It may be constant in case V and UK are orthogonal. Okay, so it's an increasing, or non-decreasing might be a better way to say it. Non-decreasing sequence bounded above, and so it has to converge. Okay. Again, that's a consequence of the completeness of the real numbers, which is something we are not going to prove, that the real numbers are complete. So this series does converge, and therefore this series converges, and we have our projection theorem. So here's a summary. H is a Hilbert space, S is a Hilbert subspace of H that has a countably infinite orthonormal set with this property, that the span of O is dense in S. That's another way to say this. Then the Fourier expansion, or whatever you want to call this, extended Fourier expansion, converges. And so the Fourier expansion is, as we have just proved, the unique orthogonal projection of V onto S. That tells us, as it did in the finite dimensional case, that V hat is independent of the choice of the orthonormal. I have to be a little careful. The orthonormal set O and the vector V minus V hat, which we will call the residual vector. That's just the definition of residual vector V minus V hat. The projection theorem holds. So got V's here when I should have H's. I apologize for all these silly mistakes. This happened because I did a cut and paste from the finite dimensional case, and I didn't update some of the symbols. So anyway, this is the decomposition of any vector into a vector in S and a vector in S perp. So the projection theorem holds. We also have, as is the case in the finite dimensional case, that V hat is the closest vector to V from within S, and that Bessel's inequality continues to hold. And these are proved in the same way they are in the finite dimensional case, so I don't need to redo that. So that is the situation. By restricting attention to Hilbert spaces and Hilbert subspaces, we were able to show that the projection theorem can be extended to any, well, let's say at this point, any Hilbert subspace that has a countably infinite orthonormal set with this property. And as I said before, we're going to show that this means that O is a Hilbert basis for S, the subspace. We're also going to show that all Hilbert bases have the same cardinality, just as is the case for the Hamel bases, the vector space bases. And so we can define the Hilbert dimension. And so how this could have read, although we're not ready for that, is simply that S is a Hilbert subspace of countably infinite Hilbert dimension. So that shows how we've extended from the finite dimensional case to the countably infinite dimensional case. What we give up is that the orthogonal projection is no longer a finite linear combination of basis vectors. It is the limit of, or an infinite sum in the Hilbert basis vectors. Let's now take a look at the last remaining case, the uncountable case. So we are dealing here with a Hilbert space H and a Hilbert subspace S that has an uncountable orthonormal set whose span is dense in S. I'll repeat that at the appropriate time. But in order to discuss this case, we're going to have to deal with uncountable orthonormal sets, such as this set here, for which the C-span of the set is the subspace in question. And so to deal with this situation, we're going to need to deal with sums of uncountably many terms. This is a subject I really don't want to get into in any real detail because it will take us even farther away from linear algebra than I had intended. So what I'm going to do is just give you the gist of things, and then we'll get to the main points. First of all, we need a definition for convergence of uncountable sums, and here is the definition. Let F be a family of uncountable size of vectors in an inner product space. This sum converges to a vector V, written in the usual way, if for any epsilon greater than 0 there's a finite set I of indices. K is the index set for the sum. So a finite set of indices for which any finite set of indices that contains I will have this behavior. The sum over that finite set of the vectors vk will be within epsilon of the limit v. Now, I suppose many of you are going to say, where did this come from? And it's a little bit difficult to explain without getting into more mathematics that I don't want to do. There is such a thing as a net in any topological space, and nets can be used to define convergence, and that is where this comes from. So it's way outside the context that we're in here, and so I'm not going to go into that in any detail. It's fortunate that the uncountable sums have familiar properties that we're used to when we're dealing with finite sums. For example, if we have two uncountable families of vectors in an inner product space, and if both sums converge, say, to x and y, then for any scalars r and s, the sum of this linear combination is equal to rx plus sy. And also we have continuity. Remember, these sums are limits, so we have continuity in both coordinates. There is a very useful Cauchy type description of convergence in this context. By the way, maybe I should mention that it's not so easy to find this information. If you decide you want to learn more about it, I think you'll have some trouble finding this discussion in other sources. I think that you probably will have to turn to books on topology in order to get more information on this. And books on analysis tend, in my experience, not to deal with uncountable sums since they don't appear that often. Okay, so here's the Cauchy type description of convergence. F is a family of vectors of any size in an inner product space V, if the sum converges, then for any epsilon greater than 0, there exists a finite set I, again, set of indices, such that if J is a finite set that is disjoint from I, then this sum is less than or equal to epsilon. So that's quite different from the definition where J contains I. Here J is disjoint from I. If V is a Hilbert space, then the converse holds, and that is this sum will converge if and only if this Cauchy-like property holds. This is the property that we will see is a bit easier to work with, which is why I included this. I'm not putting in information here that we don't need, just for completeness sake. I'd like to, but it's just too much to do that. The proof here is a bit long, but not terribly difficult. If you have the book, I recommend you read through it, see if you can do it yourself, and then if not, read through it. Now here comes a welcome bit of news. The following theorem tells us that convergence of an arbitrary sum, in particular an uncountable sum, implies that only countably many terms can be non-zero. So the sum can be reduced to a countable sum by casting out 0 terms. So that's rather comforting, because it tells us we can, in most senses, replace an uncountable sum, a convergent uncountable sum, by a convergent series in the usual sense. Although we do have an issue with order that would have to be addressed, and again, that's not something we need to go into. This proof is quite short. It's just 1, 2, 3, 4 lines, so I will leave that for you to ponder if you are interested. There is then an analog of a theorem that was critical in the countably infinite case, and that is this uncountable sum will converge if and only if this uncountable sum of real numbers will converge. And when they do, we have an even greater extension to the Pythagorean theorem. This proof is also relatively short. So armed with that information, we can return to the discussion of the projection theorem. Suppose that S is a Hilbert subspace of a Hilbert space H, and that S contains an uncountable orthonormal set whose C-span is all of S. So this is the exact setup we had in the finite case and in the countably infinite case. And we want to show that the projection theorem holds, or equivalently, just as before, that for every vector V in H, there is another vector S, little s, in S, for which the difference is in S perp, so that again we can decompose every vector. Now, the linearity and continuity of the inner product imply that we only need to show that V minus S is orthogonal to the vectors in O, for the same reason as before. And that gives us this set of equations. Now little k ranges over the uncountable index set. Same situation as before. So again, we would like to take S to be the Fourier expansion of V, which is now an uncountable sum. And as before, we face the question of convergence. Again, if this sum does converge, then there are only a countably infinite number of terms that are non-zero, and so we can cast out the rest and re-index so that the terms are indexed by the natural numbers or some part thereof. And we can write this, and we are exactly back in the countably infinite case. So that's the situation, and here it is summarized. This should look the same as the countably infinite case, except that O is now an uncountable set. And the Fourier expansion is an uncountable sum. Okay, so let's get back on track here a little bit. In proving the projection theorem, we assumed the existence of an orthonormal set O in the Hilbert space that was either finite, countably infinite, or uncountable, depending on the situation we're dealing with, and for which the subspace S in question was the closure of the span of O. So these sets O are clearly important. They take the place of vector space bases for S. A vector space basis would be linearly independent and span O. These sets are more than linearly independent. They're orthonormal. They don't span S, but they are dense. Their span is dense in S, so it's as close to spanning S as we're likely to get in these situations for the infinite cases. Well, actually the sets O, I think I may have mentioned this, for which this holds, are nothing more or less than the maximal orthonormal subsets of S. That is to say, the Hilbert bases for the subspace S. And here is the theorem. O is an orthonormal subset of a Hilbert space H. Now I'm not mentioning the subspaces here because H could be S in this context, but I just wanted to state this in general without committing to a particular subspace of a Hilbert space. So for any Hilbert space, the following are equivalent. O is a Hilbert basis. So what's missing is, well, let's go on. O is a Hilbert basis for H. O perp is trivial. The span of O is dense in H. That's the important thing for us here. For all vectors V in H, V is equal to its Fourier expansion. And equality holds in Bessel's inequality. Okay, so again, the important point here for us is we are looking for orthonormal sets that do this, where H in this case is replaced by the Hilbert subspace S. And what this theorem tells us, among other things, is that they are precisely the Hilbert bases for S. As to the proof of this, the set O is a maximal orthonormal set, in other words, a Hilbert basis, if and only if no non-zero vector in H is orthogonal to O. If there was such, then we could enlarge O. If we can't enlarge O, there's no such vector. So that holds if and only if O perp is trivial. So 1 and 2 are equivalent. The projection theorem looks like this. So our subspace S is the C-span of O. And this tells us that C-span of O is all of H if and only if C-span of O perp is trivial. But C-span of O perp is the same as O perp. We proved that a while ago. So that means that 2 and 3 are equivalent. And I would have liked to have been able to give at least that much of this theorem earlier, before we started discussing the projection theorem. But I couldn't, because we need the projection theorem to show that those are equivalent. There may be another way to do it, but this seemed to be the cleanest way. The projection theorem also tells us that for every vector v in H, we can decompose v this way. Again, I got my v's here. Okay. And where this difference is in O perp. And so v equals v hat if and only if this portion is 0. In other words, if and only if there's nothing in O perp. Now, I'd be clear on this. V equals v hat for all vectors, if and only if O perp is trivial. Okay. So 2 and 4 are equivalent. Finally, it's certainly clear that 4 implies 5. If the vectors are equal, their norms are equal. Conversely, if 5 holds, then the norm squared of v hat is the norm squared of v, that's 5. And this can be written this way, and we can use the Pythagorean theorem to split. And so this is 0, which means v equals v hat. So 5 implies 4. Here's a result that I sort of tossed in. We already know that when S is a finite dimensional subspace of an inner product space, that the second perp is the subspace itself. Something similar does hold in a more general context of Hilbert spaces. If S is a subspace of a Hilbert space, then S double perp is the closure of S. And so if S is a Hilbert subspace, it's already closed. That's what Hilbert subspace means. And so S double perp is equal to S. So we have a direct generalization from finite dimensional subspaces of an inner product space to Hilbert subspaces of a Hilbert space. So just to summarize where we are now, we've really accomplished 2 important goals. First, we know that the projection theorem holds for all Hilbert subspaces of a Hilbert space, for all closed subspaces of a complete inner product space, regardless of dimension. As a consequence, we also know that the Hilbert bases, the maximal orthonormal sets for a Hilbert space, can take the place of the Hamel bases of the ordinary vector space bases, especially when the space has non-finite dimension, in the sense that the span of O is if not equal to H, is at least dense in H. So, in a way, we give up on unwieldy vector space bases, uncountable ones in particular, in favor of maximal orthonormal sets, Hilbert bases, which may be quite a bit smaller, easier to work with. But the price we pay is that we can no longer say that we can reach all the vectors by linear combinations. We have to say we can reach all the vectors by limits, by infinite sums of vectors. I want to conclude this discussion with a discussion of Hilbert dimension by showing that all Hilbert bases of a Hilbert space have the same cardinality. We can define the Hilbert dimension of the Hilbert space to be that cardinality. So here's how this goes. If H has a finite Hilbert basis, then that set is also a Hamel basis. And so H is finite dimensional, the ordinary dimension, which means there can be no infinite Hilbert bases because they're linearly independent sets, and also that all finite Hilbert bases have the same size, namely the dimension of H. So we only need to address the problem of Hilbert spaces that have infinite Hilbert bases. So suppose we have two such Hilbert bases. For each of these B vectors, there's a sequence in the span of C that converges to that vector. Call it B sub k. So let's write x sub kn converges to bk. The x sub kn's are in the span of C, linear combinations of C vectors. Each of those linear combinations involves only a finite number of C vectors, and so altogether, if we toss, let's say that's ckn, if we toss those finite sets of C vectors together, one set for each term of the sequence, we get a set C sub k of C vectors. They are this is the countable union of finite sets, and so is countable. Now we scan through all of the B vectors, where they go, B sub k, we pick up all these countable sets, throw them together. So this is all the C vectors involved in all these sequences, converging to all the members of B. The fact is that this must actually be all the vectors in C. U must be C. Because if a vector little c in script C did not belong to this union, then we could pick up all of B with the C span of this set. Script C, throw away the little c. But the C span of B is H, and then the C span of B would be contained in here. So we'd have this string. In other words, the C span of this set, this proper subset of C, would be all of H. But little c is orthogonal to everything else in C, in script C. And this is equal to this, which is H perp, which is trivial, and we have a contradiction. So when we gather together all the C vectors that we needed to approximate all the B vectors, we get every C vector. So the cardinality of C is the cardinality of this union, but each of these terms in the union is countable. So it's of size at most, Aleph naught, and we have cardinality of k of these. So this is a formula we proved in when we discussed cardinal numbers a long time ago. This then, because k is infinite, this has size. Remember we said that the product of two cardinal numbers is equal to the maximum. So this is the cardinality of k, which is the cardinality of b. So the cardinality of c is less than or equal to the cardinality of b. But this is a symmetric argument, so we have the reverse inequality as well, and the Schroeder-Bernstein theorem tells us these cardinalities are equal. Now we're going to return to standard linear algebra. We're not done with inner product spaces. We have some very important things to discuss, and we're going to go back to that.